Hi, we are now going to study circuits with linked capacitors. What are linked capacitors? How are they different from independent capacitors? To understand that, let us look at these two circuits. Both these circuits, if you notice, they have two capacitors, the same value capacitors, C1, C1, C2, C2. And they have the same battery, right? So what's the difference? The difference is how these capacitors are connected to the battery. Here, these capacitors are connected like that. Here, these capacitors are connected in a different way. And that is going to make a huge difference. Okay. To understand what difference it makes, let us focus on this circuit first. I'm going to look at this capacitor. Now, this battery pulls a charge Q1 from this plate and deposits that charge Q1 on this other plate. You can see the path. Q1 is going to travel like that. Now, because Q1 is pulled out of this plate, and I'm going to assume that all the capacitors are initially uncharged, okay? I'm going to make that assumption. So, because it was initially uncharged and I pulled out Q1, that means this plate is going to now have a charge of minus Q1. And because this Q1 came and got deposited here and this was initially uncharged, now it's going to have a charge of plus Q1. Now, does Q1 depend on C1? Yes, of course it will depend on C1. Does it depend on E? Yes, of course it will depend on E. But what do you think? Does it depend on C2? No. We didn't even bother about C2, right? So this battery is going to pull Q1 and deposit it there. So Q1 depends on this C1 and E. It doesn't really depend on C2. To understand what happens with C2, let me gray this out and focus on C2. This battery is going to pull a charge Q2 from here, and it's going to take it around like that and deposit it on the other plate. Now, because Q2 was pulled out like that, this plate is going to get a charge of minus Q2. And because we deposited it here, we are going to have a plus Q2 on this plate. Now, notice this Q2 moves through this way independent of Q1. Q1 does not affect Q2, Q2 doesn't affect Q1. Capacitance C1 doesn't affect Q2, C2 doesn't affect Q1. So we can say that C1 and C2, they are both independent of each other. They do not affect the charges on each other. Okay. Separately, you can look at this loop separately without worrying about that. And similarly, you can look at this loop without worrying about this. So this is very important to understand. But isn't that the same here also? No. Here there's a huge difference. Let us try and understand this. This battery is going to pull charge from here, right? From C2's plate, it is going to pull charge. Let's say Q. But where can it put it? Let's see. Q comes out, Q comes this way. Well, it is going to go and land up on C1's plate. So the charge was pulled out of C2 but deposited on C1. So clearly these two are connected. They are linked, right? And because I pulled it out like this, it was all initially uncharged. I'm assuming that. So this plate has a charge of minus Q and this charge comes and gets deposited here. So this plate has a charge of plus Q. They are linked. Okay. Now because this is plus Q, this plate must have minus Q. How will it get minus Q? So basically Q must run away like that. If Q runs away that way, you're going to get a minus Q. But think about it. If Q runs away, where can it run? There is no other path anywhere. It has to run to that plate. And if it runs to that plate, that means it's going to deposit Q onto that plate. So that plate is going to get a plus Q. That's what you should get, right? If this is minus Q, this must be plus Q. So everything is consistent. But what I want you to observe is that the charge being pulled from there gets deposited here. And whatever charge runs from here goes and gets deposited there. So clearly the charges on C1 and C2, they are linked, right? You cannot have C2 getting separately charged without worrying about C1. So that means they are clearly linked. So in this situation, C2 affects the charge on C1, C1 affects the charge on C2. So C1 and C2 are linked. Whenever you have this kind of situation where two capacitors are linked, if you draw a loop like this, you will see that you can draw a loop where everything is inside. There is no path outside. There's nothing to go out, right? That's why this charge cannot go outside anywhere. There's no way for it to go. It can only go and land up there. So this loop tells us that this is an enclosed space. So charges from this plate can only go to that plate. Now you know about charge conservation. So the net charge, since there is no charge that can come from outside or go outside, the net charge inside this loop must be conserved. So inside the loop, the charge cannot change. The total charge cannot change. It can run from this plate to that plate or from that plate to this plate, but the total cannot change. And since I told you initially it was uncharged, what was the total? 0. So the initial total was 0. And what about the final? Minus Q plus Q, it is still 0. So initially the charge was 0. Finally also the charge has to be 0, because there's no way for the charge inside this loop to go anywhere or any charge from outside to come inside. Okay. So in this situation, of course, both these capacitors have a charge of Q, right? So both capacitors have the same charge. Does that mean whenever you have linked capacitors, they must have the same charge? No. In this case, it happened to have the same charge. But whenever there are linked capacitors, there is a connection between the charges, but does not mean that they must have the same charge. Let us see this with a different example. We have already learned how to use the charge flows to find the charges on the two linked capacitors like that, right? Let us try to use the same kind of thinking for three linked capacitors. So here this battery is going to pull a charge Q from that plate, and it is also going to pull a charge Q dash from this plate. And what is going to happen? These two charges, Q plus Q dash, is going to go through the battery and gets deposited on this plate of C1. Now, because this charge is Q plus Q dash, clearly you can see it is connected to these two capacitors, right? The charge on this capacitor is connected to these two capacitors. So I'm pulling out Q. I'm going to assume that all the capacitors were initially uncharged. So that means this was initially uncharged. I have pulled out Q. So this plate is going to have a charge of minus Q. Since I have pulled out Q dash from here, this plate is going to have minus Q dash. And since I have deposited Q plus Q dash, this plate is going to have Q plus Q dash charge. Now let us ask, if this is Q plus Q dash, that plate must have minus of Q plus Q dash. How will I get that? Well, so that means you must have a charge Q plus Q dash running away like this. When it runs away, this is going to leave this plate with minus of Q plus Q dash. But when it runs away this way, how much will go there and how much will go here? Because you see there are two paths. In this situation, whatever runs away, there is no other path, so it has to go and land up. But here, there is a branching. How much will run to this plate? You see this is minus Q, so this must be plus Q. So Q must run in here. Similarly, this minus Q dash, so this must be plus Q dash. So Q dash must run here. So this Q plus Q dash must split this way. Q that way and Q dash this way. And so this plate is going to get plus Q, this plate is going to get plus Q dash, plus Q dash. And it makes sense, right? Because this capacitor must have Q dash minus Q dash, this capacitor has Q minus Q, and this capacitor has Q plus Q dash minus of Q plus Q dash. Okay. Now if you notice, these two capacitors, their charges, let us say Q and Q dash are independent. But what about this? Clearly that is not independent, right? Because it is Q plus Q dash, so it is dependent on these two. So clearly these capacitors, their charges depend on each other. So we can say that these are linked capacitors. Okay. So here I have used the charge flow to figure out what is happening. But because I know that they are linked capacitors, immediately I can say for linked capacitors, I can draw a loop like that, which encloses that portion entirely with no path outside. Can you see? Nothing, no path outside, no path coming in. So you can't have charge coming in or going out, right? Whatever charge is inside that loop stays there. Can I similarly draw a loop like this? Yes. This plate, right? This plate, they're all connected. You can draw a loop around these three plates, and there is no way for it to go out or come back in, right? The charge cannot go out or come back in. You can understand that much better if I remove the charge flow. So let us get rid of the charge flows so that you can focus just on the plates. Initially, remember, all these capacitors were uncharged. So initially the total charge inside this loop was 0. What about now? Now this is minus Q plus Q. What is it total? Still it is 0. So we can say inside the loop, the total final charge is equal to the total initial charge. Initially it is 0. Finally it is minus Q plus Q, which is 0. What about here? Here also initially it was uncharged capacitors, right? Remember that. So this plate had 0, this plate had 0, this plate had 0 in the beginning. So total initial charge, 0. But here also inside the loop, there is no way for charge to come in or go out. Charge is conserved. So total final charge must be equal to total initial charge. What is total initial charge? 0. What about total final charge? This charge plus that charge plus that charge. So minus of q plus q dash plus q plus q dash. Clearly everything cancels out. You see that it's going to be 0. So remember that the total charge inside the loop cannot change because there is no path from the loop outside, right? So no charge can come in, no charge can go outside the loop. So for closed loops with no path for charges to go out, the total charge inside will remain the same as what it was initially. Okay, initially and finally the charge will have to remain the same. It can of course run from here to there, can run from here to there. This and this can together send the charge there. All that can happen. But the charge has to stay overall inside this loop. That is charge conservation. Now of course, let me put my charge flows back. We use charge flows to find out the charges on these capacitors, right? So we can use charge flow. That is one method to find out how much does each of these capacitors have as the charge. But we can also use charge conservation because that's going to give us a shorter method to find out how much charge. Because the moment I know that this plate is Q, this plate is Q dash, charge conservation will tell me that this plate must be minus of Q plus Q dash. So that's going to be a faster approach to finding how much charge each of these capacitor plates has. So both are equivalent methods. We have already seen the charge flow method. Let us now look at charge conservation method. Let us now learn how we can use charge conservation to find out the charges on linked capacitors. Okay, so let us look at this circuit. C1, C2, C3, they are linked capacitors. How do I know they are linked capacitors? Whenever you can draw a loop like this, where everything is inside and there is no path outside, that means these capacitors are linked capacitors. We will come to that in a minute. But first what I'm going to do is I'm going to say C2, this capacitor has a charge Q. I'm assuming it has a charge Q. So let us say that this plate is Q. So the opposite plate must have minus Q. So I've assumed the charge on C2. Now what about C3? Let me say that C3, this capacitor has a charge Q dash. So the top plate has Q dash and the bottom plate will have to have minus Q dash. Well, I'm only assuming, right? Now, does it mean that for C1 also I'm going to assume? Well, I can assume if I want to. Let us say that this has a charge Q double dash and so this will have minus Q double dash. But here I have not found anything. I only assume that this has a charge Q, Q dash, Q double dash. We are now going to use charge conservation to figure out what is Q double dash. Because you see that this plate, this plate, this plate, you can draw a loop like this around it. That's what makes them linked. And so the total charge inside this loop, there is no path from outside, right? So it cannot go outside, it cannot come in. So the total charge inside must be conserved. There is no path out of this loop, right? Now this is vacuum, right? Between the capacitor, it is an insulator or vacuum, right? Dielectric or vacuum. So obviously charges cannot flow through that. Charges cannot flow this way, cannot flow that way. They can flow from this plate to that plate or to this plate, right? But they all have to be inside the loop. So there is no path out of the loop, which means inside the loop, the total final charge must be equal to the total initial charge. But we started with initially uncharged capacitors, not a requirement, but we generally start with initially uncharged capacitors. So what was the total charge? Initially it was 0. So that means the total final charge, which is Q plus Q dash plus Q double dash, must be equal to 0. Which means Q double dash must be equal to minus of Q plus Q dash. So I don't need Q double dash. I can replace Q double dash with minus of Q plus Q dash. Well, if this is minus of Q plus Q dash, this must be plus of Q plus Q dash, right? Just simply Q plus Q dash. So I know the charge on C1 in terms of the charges on C2 and C3. I don't need a third variable. This statement, which is from charge conservation, eliminates the third variable. So that means using charge conservation, we can find the charge on the third capacitor in terms of the charges on the other two capacitors. It reduced one variable. Okay. So remember that here I assumed that the capacitors were initially uncharged. If the capacitors were initially charged, you can still use it. Just that the total charge inside the loop would not have been 0 because they were initially charged. So whatever it was initially, you just add that up. Instead of saying that Q plus Q dash plus Q double dash is 0, you will say Q plus Q dash plus Q double dash is equal to the initial charge. That's all. That will be the only change. That still means Q double dash can be found in terms of Q dash and whatever was the total initial value. That's all. That's all will change. The total final charge inside the loop is always equal to the total initial charge inside the loop. So remember that using this, I don't need to know how the charge flows. I can directly find the answer, right? Once I say this is Q dash, I know that this must be, in this case, because it was initially uncharged, in this case I can say this must have been minus of Q plus Q dash. So this must have Q plus Q dash. So you can quickly find the charges on each of the capacitors using charge conservation. Okay, now we have learned two different methods, right? We have learned charge flow method, which is a little more cumbersome, little long, and we have also learned charge conservation method. Charge conservation is clearly faster. But there is a third method, which is, I am calling it Kirchhoff's charge law. Okay, basically you are going to apply to this junction charge flow, but you're not going to do it for the entire one. You're going to look at this loop and you're going to take just one junction in the loop and you're going to apply. It's going to be quite an easy method.